So now it's time to go through and actually figure out where our electrons exist or where are electrons in our atom. Before we get into that, we really have to have some understanding of how we discovered where electrons came from and really, or where electrons exist. And where that started is looking at light, because it's how light interacted with matter, or rather how matter produced light, that we get an understanding of where our electrons are. So really, really simple basics. Don't stress about numbers or equations. Light travels as a wave, and waves are defined by really two pieces: a wavelength, which is the distance from peak to peak, and then also the frequency, which is the number of wave cycles completed in a particular interval of time or distance. So if we take a look at the image below, what we've got are some potential pictures to represent this. So if we're looking at a long wavelength, the distance between peak to peak, that's now representing our wavelength. If we look at the one underneath it, that peak to peak distance has now significantly changed. Okay, so we're looking at a long wavelength. Wavelength is typically represented by a lambda, or a short wavelength down below. The next thing that we could look at is within an individual interval of, say, time. So let's go ahead and pick a starting point in both cases, and we'll pick an ending point, same time. How many peaks cycle through that, or how many cycles do we get? So for the top one, 1, 2, and then we hit 3. For the bottom one, 1, 2, 3, 4, 5, 6, 7. So the bottom one has a higher frequency because there's more cycles that move through. Wave nature, or the wave properties of light, can be tied back through energy, and that's where we get that equation E equals H, and then the symbol for frequency is the Greek letter nu. You don't need to stress about that, but physicists came through and established that relationship, and so we do fully understand that there's energy associated with these, and it's tied to the number of peaks, our frequencies. One of the things that's kind of fun to recognize is there's an inverse relationship between frequency and wavelength, which if you advance through more advanced chemistry classes, you'll probably be expected to recognize that and be able to interpret that pretty quickly. So longer wavelength means shorter frequency, and shorter frequency means, or sorry, longer or larger frequency means shorter wavelength. Okay. So within that, what we're looking at is what's known as the radiant energy spectrum. So when we think about light, invisible light, it's really this tiny, tiny little section of our energy spectrum. That's this section right here, visible. And we may think it's this big grand thing because of all the great colors that we go through and see, but really, those are all very subtle variations in energies, and we've just developed eyes that allow us to see those subtle variations in energy. And we've called that the visible spectrum because that's what we can see. If we think about it, if we had something that could respond to more energy things, or we'd get less nuance or less detail within that color spectrum. And we'd probably start seeing things as larger blocks and not as kind of gradations as cleanly. Theoretically, maybe. I don't know. I'm just kind of making things up. So what do I want you to get out of this? Well, I want you to recognize that the visible light spectrum is a tiny section of our radiant energy spectrum. It goes all the way up to cosmic rays at the extreme high energy, and it goes all the way down to radio waves at the extreme low energy. Right? And so we're kind of bounced somewhere in between. And what becomes important is that because they have varying energies, they're going to cause different things to happen. Like you got hit with cosmic rays, it's going to cause you to disintegrate. Right? There's just so much energy within that you just aren't going to be able to withstand that at a molecular level, and you kind of fall apart. That's why when Hulk gets hit with gamma rays, he kind of gets destroyed and his whole system gets rearranged. Really, it would just result in a puddle of goo, not a now crazy strong behemoth of a person, but, you know, who's to say anything to the comics? And if we push to the opposite end of the spectrum, our radio frequencies are insanely low energy, right? But that low energy is still energy, and we can detect that if we have the proper equipment, okay? So other things to nail down on this is that range of energies, high to low. So I do expect you to know that that red light, visible light, is low energy. And I do expect you to know that that purple light is high energy, okay? So it might be useful to have some way to differentiate and understand or memorize these relationships. For me personally, only recently did this kind of strike me. Purple, also known as violet, is very close to the ultraviolet side of the spectrum. Red is very close to the infrared side of the spectrum. So if I'm going to try and figure out which one is higher energy, melt my face versus listen to some tunes in the car, which one's closer to the melt my face end of it? Well, clearly the cosmic rays are, but you're looking at the picture, right? If we remember ultraviolet and infrared, when we go out in the Arizona heat in the middle of the summer, one of the things that we're concerned about is UV radiation, UV for ultraviolet. Why are we concerned about it? Because it causes cancer. How does it cause cancer? It literally causes atomic or molecular degradation, which can potentially result in cancer cells. Right? So it's exceptionally high energy. The infrared, while it may slowly cook me, isn't really resulting in any kind of molecular degradation. So the closer I am to that ultraviolet end, violet color, the more likely I'm to be hit with high energy. Okay, whereas the red, as far away from ultraviolet as possible, or close to infrared, is now the low energy. That in and of itself isn't a big deal, but now what if I say yellow? Okay, and you're like, well, yellow is just a color. I know, but where is yellow on that spectrum? Okay, is it lower energy or higher energy? And this is where you're like, well, clearly it's closer to red, right? Well, before you're being too much of a smart aleck on that, you're looking at a picture. Right? What happens if that picture disappears? Do you now still have that same ability to know where yellow is relatively on the scale? If you've memorized the colors of the rainbow, you're probably set. If you haven't, you've got a bit of a problem. Okay? How most people seem to go through and memorize it is the acronym for a person, Roy, and yellow was probably a bad idea, Roy G, come on, pen, work with me faster, Biv. And I don't really know what color indigo is, so I'm just going to call it that kind of purple. And we've got our red, orange, hopefully I'm spelling these roughly right, yellow, green, blue, indigo, and violet. Okay? And that helps us to remember the sequence of those colors. Okay? On top of that, remember the part that's actually important is knowing not just the sequence of the colors, but which one's high and low energy. Okay? And that's where you could go through and remember that U, or the violet, is close to UV, and that is our high energy. If you now have this, okay, memorized, you can very quickly come up with a ranking system for this if you were asked for which of the colors is the highest in energy. Okay, and that's kind of the point behind this. Because we can't really control your notes for exams, it might not be a bad thing to have written down. Just realize the more stuff you have to search through on an exam, the more likely you're going to do poorly on the exam. So spending some time to memorize some things is probably a good idea. Okay? And so with that, we've got the basics of what I want you to get out of the radiant energy spectrum. We have our visible light that is broken down into a continuous spectrum. So it's continuous. There aren't, say, black lines in between each of these things. Okay, there's not like a black bar in there. Okay, while we may have gone through and memorized it as Roy G. Biv, it's a gradual transition all the way through. There's still fire engine red. There's orangey red. There's orange, orange, red. Okay, there's all those blends of colors within those. And so we can't definitively say this is blue, this is green, this is yellow, or any one of those colors. We arbitrarily put those lines on it because that helps us to distinguish those. Okay, that's where we're seeing those biggest kind of scale differences. Red versus clearly orange in between. So that's kind of the idea behind it. Okay, so with that, wrong buttons, we can go ahead and continue on. So why has this become important to us? Well, remember how we had those vacuum tubes, okay, that Thomson was playing with. Well, some other people started playing with those and said, well, what happens if we put in a small amount of some other gas? What happens if we pump 20,000 volts through it? Okay, this is kind of the forebearer of your neon signs. If we go through and do that and pump 20,000 volts through, we see this cool light that comes out of it. And in the case it's being shown here, if I take a lamp, okay, or a tube, remove all the air except a little bit of hydrogen, and I pump 20,000 volts through it, it glows this kind of cool purpley color. And that in and of itself isn't a big deal, except of course people played around with light, and we have these things called prisms, and prisms will divide the light out into the individual colors that made it up. And so if we saw a purple light, what we might expect to come out of the prism would be just this kind of purple color at the end. And there we go. We'd be like, oh, it's just purple because that's what I'm seeing. But we didn't see that. Okay, and that's what this is showing. We didn't see just a smattering of purple color. What we saw was 3 lines. Okay, what we're trying to do with that term of line is be very, very specific that we're seeing a very thin band of color. So when we're talking about purple light, we might say purple light would be seeing everything like that. That would be purple and would be kind of continuous within that. We're not seeing that. What we're seeing is this very thin band of purple, green, and red. And that seems a little bit weird to us. Okay? Why would it divide out like that? Well, part of this is going to come back to where's that light coming from? Okay? And where it's ultimately coming from is our electrons. Right? The light that we're seeing here isn't enough to disassemble the entire atom, okay? Because we still have hydrogen at the end of this process. So something must be changing within the atom, but then staying the atom. So something has to be moving around and relaxing back, right? If it's the nucleus and it's moving around, we're probably going to see new atoms because the nucleus has protons and neutrons. And if I'm messing with the nucleus, I'm probably doing some kind of fission or fusion. I always get them backwards. I think it's fission, okay? And that would be a little bit more than just some pretty lights, okay? So it's not protons, it's not electrons. Well, or sorry, protons or neutrons, which means the only thing left is really our electrons. Well, where did we say our electrons existed? Okay, and to this, really what I want you to do is think about what we said our atomic model was at this stage in the game. Well, we said we had some protons with some neutrons in a nucleus, okay, that were itty bitty 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 bitty, and then we had this giant thing on the outside, clearly not drawn to scale, that represented the size of the atom. Well, that size of the atom was where our electrons were. Well, where in that? Okay, right now, all we've said is they could exist at any point within this. Right? And we might predict that it would be lower in energy if we moved the electron closer to the nucleus, because if it's closer to the nucleus, those charges cancel out. Right? So that might be a predicted low energy state. Okay? And a very high energy state would be as far away from the nucleus as humanly possible. Okay? And we're really just saying that electrons exist anywhere in there. Right? So if we're thinking about electrons moving, if I pump 20,000 volts into that electron, it could jump all the way up to here. Well, that's now the jump. Right? And for those people that are like, why would it jump? Stick a cattle prod in your closest friend's patootie and see what happens. don't do that. I'm gonna need to, don't do that. That's not good. But you can pretend in your head. Okay? If you did that, they're gonna jump. Same thing's gonna happen with our electrons. So why is that important for us? Okay? Well, that means that the electron is now at a high energy state. Okay? And eventually, what is your friend gonna do? Well, he's gonna relax back down. Your friend probably won't hate you for life. I guess it depends how big of a cattle prod you got. Okay. And as it relaxes back down, well, that's now dropping to a lower energy state. It was able to jump up because of the 20,000 volts. When it goes back down, where did all that energy go? That energy went into light. And that's the light spectrum we're seeing, the violet, the blue, green, and the red. But if our electron could exist anywhere outside our nucleus, that means those jumps could happen any distance and any energy, which would mean we wouldn't see these lines. What we'd be seeing is a continuous spectrum of possible energies because all energy states were allowed. Well, damn, that's not true. I see lines. Right? What those lines are representing is that the electrons can only jump between certain states. That's an interesting observation. This means our electrons exist at discrete energy levels. Okay? And so this is where we get Niels Bohr coming along and saying we get electrons existing in orbits around a nucleus. Why is this different for us? Well, if I take this electron and it gets 20,000 volts, it could jump all the way up to the top. Cool. When it comes back down, it could release light. And in this particular case that we're looking at, there are two jumps that it could potentially do. It could have done that short little jump, and of course I color-coded them backwards. It could have done that short little jump, okay? Or it could have done that longer jump. Okay, larger difference in energy. So we're going to get different color light for each of these jumps. Okay, but I'm only going to get those two lights. That's it. Okay, I can't get a large smattering of different energies. I'm only going to get two things out of it. Okay, and that's referencing the discrete energy levels. Okay, Bohr's theory is kind of based loosely off of gravity, or what we would observe with gravity. It has nothing to do with gravity. Don't bring gravity into this. Okay, this is whole quantum other stuff. There aren't orbits. There's energies. They're not orbits. Okay, so electrons can exist at an energy level. Okay, and they can jump from energy level, or they can relax down to lower energy levels. But we have to have the energy to allow that transition to occur. Right? And so each of those steps is what's known as a quantum, right? What allows us to make that jump. And that's where we're getting quantized. So if we're going to look at a quantum concept, we can use this as an example for a tennis ball, okay? At the top of a ramp, when we let go of it, that tennis ball exists at every single interface. It can touch the ramp at all heights. But if we look at the stairs, it can only touch the stairs at steps. It can't exist at a half step. It's in a transition at that point. Okay, so our stairs would be an example of a quantized state, and our ramp is an example of a continuous state. A rainbow, continuous, because all of those things. Line spectra are discrete, okay, or quantized. Okay, so what does this mean for us? This gives us the existence of energy levels. So when we're looking at, in the case of hydrogen with 20,000 volts in it, what's happening is we took hydrogen that has an electron in that first energy level, and when we pumped 20,000 volts into it, that electron could jump to any energy level higher. Okay, that jump is now a higher state. We don't see anything yet. Okay, what we would have to see is now the electron at one of those higher energy states jumping back down. okay? And that's what this figure is attempting to show. Again, not to scale. If we take from the fifth energy and jump to the second energy, okay, that corresponds to violet light. Notice that's a pretty big jump. That's the fifth energy to the second energy. If we contrast that or conflict that, conflict's probably the wrong word, third energy level to the second energy level, that's a smaller jump. Smaller jump means less energy. Look at our light colors. Red was lower in energy, smaller jump. Okay? And that's what we're looking at with our atomic line spectrum, is it's the jumping between those orbitals. For those people being like, well, why did it not go all the way back to the first energy? It did, okay? But what happens if it transitions all the way to the first energy? Let's go from the fifth to the first. Is that more energy? Yeah, that's more energy. And because it is more energy, it is now gone outside of the visible spectrum, which means we can't see it, right? So we get a lot of transitions that just don't fall within the visible spectrum, right? Particular elements will respond differently to these lights, okay, or to the electric voltage applied to them, right? And how do we know that? We tested it. Okay, so we've got an example of helium, lithium, sodium, and mercury. We just looked at hydrogen, and note that we see different bands. Okay, these are typically referred to as atomic fingerprints. Astronomers use these atomic fingerprints to determine the elemental composition of stars around us. So they could aim it at the sun, or aim their telescopes at the sun, and break down the light coming back from the sun to be like, it's 90% helium. That's pretty cool. They can aim it at planets to determine how much of that light coming from that planet was due to oxygen, due to water. They can do it from molecules even. Like, it's crazy the stuff that they can pull out of this, right? And they're characteristic for an individual element. Right? Why would they be characteristic? Well, what happens is we move from hydrogen to helium. Well, we add an extra electron. Those electrons repel away from each other, which means the starting electron energy is different for helium than it is for hydrogen, right? Which means each of the jumps is different, which means we're going to get a different fingerprint. That's just looking at the electrons. What else changes? You got more protons. More protons, stronger nucleus. That's also going to change the energy of your electrons, because now your electrons are going to get attracted to that nucleus a little bit more. Right? And so we start to get massive changes in where those individual jumps are. So they aren't always going to the second, they aren't 5 to 6 or any particular thing. They're particular for an individual atom, or not atom, for element, and that's why we see these things as fingerprints. So why don't we just use fingerprints all the time? Well, you didn't fingerprint me. I'm sticking my finger up, there it is, to the camera. That doesn't work to fingerprint me very well to identify I'm I could just be some random dude that someone just threw a picture up, and you don't even know if I'm your teacher, right? You're just taking some things based a little bit on faith in some of that presentation. And so we would see how those individual atoms would interact in another environment. That would be an easier test than trying to do the atomic line spectrum, right? And so that's why we don't go immediately to our fingerprints. Okay, but ultimately, what do our atomic line spectrum give us, or the emission line spectrum? They tell us we have electron orbitals. Okay, so our electrons can exist outside the nucleus, but only at particular stages or steps. Okay, so let's look at where our electrons can exist. Okay, because I remember how I've got this slide figured out, we're going to say the nucleus of our atom is way off the bottom of the page. Okay, so just for scale's sake. And right now we're really just, and for scale's sake, we'll look at the highest energy. Okay, because remember, the electron's attracted to that nucleus. Eventually, you're going to take that electron so far away from the nucleus that it's no longer associated with the atom. Well, if it's not associated with the atom, Where is it? Remember, we're only looking at an atom. If we're only looking at an atom, where it went was to the vacuum. And I always screw up spelling vacuum. So we'll just call it VAC. Okay, so that's our highest or furthest point. So we could have our electron exist at varying stages through there. Okay, it might be nice to have names for these. Right, being the super creative people we are, we might pick the lowest energy state to be a representative symbol of low. 1, 2, 3, 4. Yeah, that's how they're numbered. Okay, we've numbered that initial energy level based off of the numbers 1 through, interesting question, how many energy levels could we have? Theoretically, infinite number of energy levels. But it turns out that we run into limits. We run into that limit of that vacuum, right? And so what ends up happening is we get 7 energy levels, right? This would be a good time to take a look at the periodic table. This would be that space bar. Punch that real quickly. Take a look at your periodic table and think about that 7 number for a second. Now that you're back with me, hopefully you noted that there are 7 rows in the periodic table. Why are there 7 rows? They correspond to each of the energy levels. That's where they're coming from. That's why we have 7 rows. For those people being like, what about the lanthanides and actinides at the bottom? Those were supposed to be inserted into the larger periodic table, and I also said a little while ago, just erase those and don't worry about them. Okay, but they're technically inserted into the larger table. Our table runs a lot longer than it looks. Okay, so there are 7 rows, there are 7 energy levels. Neat. Right? So we're now talking about putting electrons into this. So let's discuss this. How many electrons do you think I can put in to an individual orbital? 1's probably a good place to start, so we could put in just 1. So I'm just going to write a 1 there. Okay. If I continue to add electrons, I'm probably going to have to go up to a higher energy level for each of these. Okay, which would mean I'd get a total of 7 electrons. Last I checked, there are 118 elements, which means I would need at least 118 electrons. This theory doesn't work for us. Okay, we're missing something. That thing that we're missing is it turns out that our electrons can be placed in the same orbital, okay, as long as they spin differently. Don't stress about the spin. Recognize that what spin means is each orbital can hold 2 electrons. Okay, so now with our newfound information, we can go through and place 2 electrons all the way up. Okay, and for those of you that can do math quick, probably can also tell me that that's only 14, not 118. So our theory is still wrong. We're still missing something. Right? This is where things go completely sideways as far as most students are concerned. And really, we're kind of expecting you to accept it on faith. Which is a bit nuanced. And it's not just blind faith. Physicists have actually proven, based off of, as proven as we can get, based off of probabilities of where electrons exist, based on wave and particle dynamics, saying what happens to each of these energy levels. Okay? So it is way beyond the level of this class. But what I will tell you is that every time you move up in an energy level, you get a new type of orbital. Okay? Well, what do I mean by that? So let's start at our first energy level. Our first energy level only has 1 type of orbital, and it turns out that that orbital looks like a sphere. Okay? When I go up to the second energy level, I get a new type. Okay? So there's my second energy level. I still get a copy of the previous one. So I still get the sphere type, but at the second energy level. But I now also introduce a new type of orbital. That new type of orbital looks like a dumbbell. Okay? When I move up to the third energy level, again, we copy sphere, dumbbell, and then we get a new shape, which was probably one of the best times I've ever drawn it, cloverleaf. Okay? So every time we move up, we get a new orbital type. Okay? Note I'm saying orbital type, right? Because even if we go through and do this for all of our 7 energy levels, we're still not going to achieve 118 electrons. right? So there's something else going on here. That something else I like to reference as an orbital orientation, right? Each of those orbital types can have multiple orientations. Each orientation results in a new orbital-ish. Okay, what do I mean by that? So let's walk through it again. First, energy level 1 orbital type. It is a sphere. Okay? If I took a sphere and turned it, would you be able to tell that it had been turned or rotated? Well, no. That's because there's only one orientation. So if I'm going to kind of move off of how my diagram has been set up, I'm going to say there is one line or one orbital, because there's only one orbital type and one orbital orientation for the sphere. When I move up to the second energy level, it's still a sphere to start with. Okay? Again, only one orientation. But the next one, that p orbital, if I turned that, would you be able to tell that I turned it? Yeah. Okay. And in fact, you might be, well, you rotated it 90 degrees. There's another one that you could rotate 90 degrees that is virtually impossible to draw, okay, where it's coming in and out of the plane at you. We've got the y, x, and z axes. Okay. And remember, this is a three-dimensional object. Turns out for the p orbital, there are three orientations, right? Which means there's three orbitals. So just looking at the first two energy levels, see, this is kind of neat. The first two energy levels, if I look at all the electrons I could place, okay, in fact, we'll backtrack. Let's look at just the first energy level. I can place 2 electrons. Go back to that periodic table for me, because I know you've got it handy because you're an awesome chemist. First row. How many elements are in the first row? I'm going to bet your answer came in as 2. We only had 2 electrons. Interesting. Let's move to the second row on the periodic table and go through and count how many elements do you see in the second row. I'm going to bet you came up with 8. Why would I bet that? Let's take a look at our second energy level. Each orbital can hold 2 electrons. There's 2, 4, 6, 8. That's kind of goofy, but it's true. Each of those energy levels is going to represent the number of electrons or the number of atoms, elements in an individual row. We do run into some goofiness that we'll talk about later, so don't stress a whole lot, but our first 2 rows are spot on, okay, for the number of electrons we can fit in. So if we're looking at our rows, we can find an element on our periodic table, we find the row it's in, that's the energy level or its highest energy electron. Okay? We can then count out where it's located in the columns to then decide where specifically that highest energy is located, be it an S, a P, or a D. Okay? Theoretically, even an F. Okay? So that's kind of crazy and cool. But we have to be able to do this kind of interplay back and forth with our electron homes and the periodic table. And that is very challenging for me to do in this environment. But we're going to attempt to do that probably in a later video though. Okay. But what I want you to recognize here is that what we are building is where our electrons can exist. Okay. And these are really just a way of referencing city, state, street, address. Right? And even for that matter, how many people are living in the house. Right? It's just an address for every single electron on an individual atom. Right? So let's walk through a couple quick examples here. Hydrogen has 1 electron. Where does that 1 electron exist? Well, that 1 electron I'm going to place at the lowest energy level, which means I'm going to be going into the first energy level. I would place it in my picture diagram like that. So I would say it's in the first energy level. It's the S type. There was only 1 electron there. So there it is. What happens if I move to helium? Well, helium now has 2 electrons. the first electron is going to be, or the past earlier electrons are copies of the previous one. So hydrogen 1s. Where's the next electron for helium go? Because it has to have two. Okay. Well, each orbital holds two electrons. I can place that second electron into that same orbital. So I could say helium is 1s, 1s. It's kind of redundant, right? Okay. Is there a way that we could condense this into a simpler format? Turns out, yes. What we can do is go through and say that this is 1s2. Okay. What does that 2 represent? It represents the sum of the superscripts. Okay. That superscript is where we're representing where electrons exist. Didn't we say something about where we represent electron locations earlier in the semester? Yes, we did. It's found in the upper right-hand corner. There it is. Our electrons are showing up in our electron configurations in the upper right-hand corner. Fantastic. Next kind of pattern I want to point out to you. First row, right? The number in front for both of those represented the row. Okay. The next one's a little bit tricky. That S symbol is typically what's known as a block. And we'll see reference to the block in the next lecture video. Okay. Within that block, we can reference the column location. The column location within the block is specified in the upper right-hand corner. Our periodic table tells you your electron configurations. There's very little to memorize once you learn how to pull it out of the periodic table. It is a bit of a cliffhanger because I'm not giving you a whole lot of information, but when you go through and try and practice these electron configurations, hopefully you'll start to notice the trends of where that information is stored and how to nuance and pull that out. Okay. With that, we're going to go ahead and push just a little bit further and look at the pictures of our orbital types. We said the sphere for our first energy level, okay, was a particular type. We could go through and always refer to it as a sphere, but that's a bit tedious. Instead, what we will refer to it as is the S type. Okay? So if I place an electron in that lowest of an individual energy level, that's known as my S type. That dumbbell shape we could always refer to as dumbbell. Okay, and the symbol that we use for that is actually P, because whoever came up with a symbol was clearly a dumbbell. And you can't look at the camera. Oh, wow. Okay, so there's S and P. We moved the last one we said was a cloverleaf shape. And the cloverleaf shape we reference as D. You are responsible for knowing what the shape is and the one-letter code that we use to reference it. What these shapes are, remember how we said they're not orbitals? They aren't orbitals. Okay, what they are energy levels. These shapes come from solving the big, messy mathematical equations for probability of finding the electron. Okay, so the S-type shape says that if I'm looking at an electron in that orbital, I will find it in that shape 95% of the time. Okay? If I look at the dumbbell, okay, 95% of the time, that's where the electron exists. So really what we're doing is that if we were to look at this pictorially, I'm just looking for the electron and just saying, where does it show up? And if I'm looking at the S type, I would see something like that. If I'm looking at the P type, I end up seeing something along these lines. Okay, and note, it doesn't have that same shape, right? There's this empty space in between. That empty space we refer to as a node. Right? If we were to jump all the way to the cloverleaf, I'm tired of my pointillism practice, okay, we'd be seeing the same kind of process. Right? So these kind of pictures that we're seeing are representations of the energy. We're talking about our orientations. The S orbital has only one orientation. Right? The P orbital, we could orient on the X, Y, or Z axes. And you can label those ultimately however you want, because it's ultimately just a frame of reference. So don't stress necessarily about those labels. Recognize that there's 3 orientations. The d orbitals, okay, the orientation model becomes a little bit trickier to deal with there, okay. There end up being 5 orientations, okay. And you might be being like, well, let's look at that d orbital. That d orbital at the very end doesn't look like a cloverleaf. You're right. It's technically a dumbbell donut. That's the name associated with it. You might, well, how the hell am I supposed to memorize all these orientations if I can't try and nail that down? Okay. This is where identifying the blocks of your periodic table come into handy. The S type, you could only fit 2 electrons. The P type, each of those holds 2 electrons, which means I get 6 electrons. The D type, there's 5 orientations, which means I get 10 electrons. 2, 6, 10. Again, think about looking at your periodic table, look for patterns, see if you can find this 2, 6, 10 pattern that we're referencing. Because I know a lot of people start to look at the rows, don't look at the rows. We already identified those as our energy levels. So again, patterns 2, 6, 10, see what you can come up with. Come on. Right? So our capacities, what this is just trying to get you to think about is how many electrons fit in each of these kind of systems. So if we looked at the first energy level, okay, there's only the S-type orbital. I can only fit 2 electrons in that S orbital, which means for the first energy level, I can only fit 2 electrons. Okay. Where this is now going to move is what happens when I move to the second energy level. Well, I'm going to get another S type, but it'll be 2S now, and I'll get a 2P type. Okay. Well, the 2S, again, one orientation can only hold 2 electrons. The 2P type, though, has 3 orientations. Each of those can hold 2 electrons. So not 222, bad joke, it's 6. Okay? Which means for the second energy level, I can fit in sum total 8 electrons. If we continued this pattern all the way up to the third, we'll just walk through that real quickly. I might stop and make you answer a question on it. 3S, P, and D. Our S have that 1 orientation, 2 electrons. Our P, 6. Our D has how many electrons? It gets us our 10, which means for the third energy level, I would get a sum total of 18 electrons. Okay. If you've been doing what I've been asking you to do, you might be noticing there's some weird discrepancies in how those patterns fall with what I've described. Right? That's because there are some weird discrepancies, and we will address that in the next video. Okay, which I believe we're kind of done here. So this just summarizes out the rest of those pieces. 4 is also on this table, and let's see. Yep, I'm right. That's exactly where I wanted to end, because the next video I wanted to review the electron configurations again. Make sure you get a comfort with that before we actually start pushing into where those patterns are found with the periodic table. You can always read ahead. Okay? Thanks for listening. Apologize for running a bit long. Oh, and I should stop the video, shouldn't I?